Okay, it's 9:40, so let's get started. Quiz 8's out. I hope you start working on that. Let's do Saturday as usual. Homework 4's out too. So, are there any questions before we start? About class or anything? Okay. So, what did we talk about last week? What was the main thing? Yeah, this pushdown automata, but what about it? What did we do with it? Yeah, we converted it into a, right? So we took a arbitrary PDA and we converted it into a CFG. Well, if we can show that this is true, we can convert a PDA to a CFG. What can I immediately then say about PDA? What do I know? Do I know something about the relation between these two already before I show this? Were any of you in recitation last week? What did we show last week? What did we do with PDAs and CFGs last week? Well, we did the reverse. We converted a CFG to a PDA. So if I can show this direction, what can I immediately say? They're equivalent, right? So therefore, PDAs recognize the CFLs. This is what I want. Okay, well, how am I going to do this? I can't just do the reverse of what we did last time because it's an arbitrary PDA. I don't know anything about its structure. It's completely arbitrary. And we don't have a normal form yet for PDA, so I can't really work with that like we did with CFGs, so what can I do? Well, let's see. Suppose we have this arbitrary PDA. And let's say it has two accept states. It may have more, it may have fewer, possibly. But let's say it has two. Then, if I'm in here and I accept, that means that I've read all the input, right? In order to accept, I have to read all the input. What does the stack start out as? It starts out empty. Does it have to end empty? Not necessarily. We didn't require it to. But could we enforce that? Maybe that might be a good idea. Maybe we can have some kind of symmetry here where I start out empty and I end empty. That might be nice. So how can I enforce that here? Yeah, so what I do is I make a new final state. And what does this final state do? What is its job? It pops everything on the stack. Does it read anything? No, because if I'm going to get to here, I better have read the input already. So I'm not going to read. I'm going to pop and obviously not push. Well, how am I going to connect that state up to the original machine? Epsilon transitions, right? But should these guys be final? I mean, they could be, but wouldn't it be nice if I have exactly one start state and exactly one final state? And we'll see why that's important. So I'm going to make these guys non-final. And then how am I going to hook it up? Via epsilon transitions. And since this is an arbitrary PDA, I don't know if there's some kind of special symbol being put on at the beginning. So I don't know at this point right here if the stack actually is empty yet. So I can't pop anything on that transition. So I'm going to save the popping here. But you then say, well, suppose the stack isn't empty, and I come over to here, And since we don't have to have an empty stack to accept, I just accept immediately. So is there a problem with that? This still may accept with a stack non-empty. Is there something that I can say about whether it could be empty? Does it have to end empty? No, if it goes to here, it still could accept if it's not empty. But what about knowing whether it accepts with an empty stack or not? Could it? Yeah, no matter what it is, if I can get to here and have read all the input, I can just read I can pop the entire stack off, and therefore I could accept with an empty stack. So all I'm doing is I'm allowing a way to have an empty stack. And we'll see why that's important. Let's see. So let's suppose that we look at the stack height over time. Well, we said that the stack height starts out at 0. So I'm going to call this the vertical axis stack height and horizontal time. And what do I know about the very last point? Well, be careful. I don't know anything about what happens at the end. But I know that there is a way for it to be 0. It could be non-zero, but I'm allowing it to be 0. So I'm looking at the computations, the accepting computations where we do end up at 0 stack height, which I'm allowed to do here. Well, let's see. Suppose that we monitor the stack height over time. Maybe it starts out flat, then it goes up, then maybe flat, then down again, up, and then maybe it does this. Okay? So let's look at this push right here and this pop right here. Do I know anything about those two things?
The one that's pushed is getting popped.
Yeah, so if I look at this push and this pop, is the symbol necessarily the same?
Yes.
What if this transition in the middle pops then pushes? Then whatever was pushed here just got popped, and then a new symbol got pushed on. So when I pop here, the new symbol gets popped off. So in general, I can't assume anything about whether the push matches the pop. And why is that? Because I have points where the stack height on a transition doesn't change. And it may be possible that this flat part was a transition that neither pushed or popped. It could be both of them. It could be one of those, right? One of those two possibilities. So what can I do to avoid a situation like that? Right, so I have to, if I can ensure that I can only do exactly one of push or pop every single time, then I'm good. Well, I think the transitions that already do exactly one of the operations, I think those are okay. So it's the other ones, the other two, that we need to worry about. So the transitions that neither push nor pop, and then other ones where they do both. And I'm not concerned about whether I read or not, so let's just say I read. I could read nothing on these, possibly. So let's look at the one where I do nothing on both. How do I fix that? So that I have one or more transitions where I do exactly one of the operations. How do I fix that? What's it?
You push first and then you pop it.
Yeah, so is there anything that I need to push? Yeah, I gotta push something. So let's just put an arbitrary symbol on. Then what do? Do I pop the same symbol or a different one? Same one, yeah. So I'm gonna break this up into two transitions where, well, let's see. I say that I read here, I might not read in general. Well, I have two transitions. I could choose either one to read. Let's just say I do the first one. And then the second one obviously is not going to read. Well, here, we can't pop something, then push it, the same thing on, because I may have an empty stack at this point right here. So what I have to do is I have to push an arbitrary symbol on. So this transition, first transition, better than not pop. And let's just say that I push on an X, an arbitrary symbol. What does this second transition have to do then? Pop the X, yeah. And obviously not push anything. Okay? So all this really is just simulation of transitions we already have. So let's do the second one, where we do both push and pop. So how can I handle this one? So maybe I can do two transitions again. This seems like a sensible idea. Well, which one do I do first? I have two operations to do. Which one do I do first? Popping, right? Do I do pushing first? No, because if this is the thing I wanted to pop originally, I push something on, now it's not at the top anymore, right? So I need to do the pop first. And let's say I do a read on the first transition. Then I'm going to pop the B first, push nothing, not read on the second guy, not pop, push a C. So all I'm doing is just simulation. Because I know that the pop happens first, I do that guy first. Okay? Any questions about that? So that's actually really nice now. Because what do we know about the very first transition when we do this? If I make this conversion, what do I know about the very first transition? It must be a push. Yep. What about the very last one? It must be a pop, because there's no way I could push to get to zero stack height. So the last guy's a pop, but in the middle it may go up and down all the way. Maybe it comes back down to zero, and it goes up. It does something maybe like that. Okay. But the key here is that it's never flat. It always goes up by one or down by one every single time, because I made this conversion. Well, maybe we can start making the grammar. So, what are my variables going to be? Well, it's not necessarily easy to figure out, but how would you find what the strings are accepted by a PDA in this PDA, for example? How would you find what strings are accepted? Right, from where? The start state. So we made sure to make a single final state so that I know that the strings that are accepted take me from the start state to the final state. But let's think about something for a second. I want to know what strings take me from here to here. Suppose I know how to get from the start state to this state, and I know from this state to this state. Do I know how to do this? Yeah, all it is whatever it takes me from here to here, concatenated with anything that takes me from here to here, right? It's just subproblems and merging them together. But may I possibly need a transition that is in the middle, that involves, that is just between two arbitrary states? May I need that transition to figure it out? Yeah, in general, I might need that. So what I need to figure out is what strings take me from any state to any other state. Okay? But we gotta ensure something else. What does the stack start out? Empty. What is it allowed to be here? Empty. So what should I ensure about going from any state to any other state in terms of the stack? It better stay exactly the same height. Because if it wasn't the same from here to here, then I can't necessarily assume that it starts empty and ends empty. So I have to think of this as any state to any other state, empty stack to empty stack. Okay? So what we're going to do is we're going to call A sub PQ with P and Q being arbitrary states. So P and Q have not necessarily anything to do with each other than the fact that they're states. Okay? So what this represents is this variable is going to generate all strings that take me from P to Q with the same stack type. Actually the same stack contents, but the same stack type for sure. Okay? So then, what is my start variable? Well, if I call this guy Q0 and QF, I think it's the things that take me from the start state to the final state. So what do you think my start variable is? AQ0, QF. So in the way that we're setting this up, because we only have one final state, I only need one start variable. Well, I can only have one, but it makes the conversion much easier when I have one final state. Okay? Well, that's dandy. And another nice thing is that the input symbols of the PDA are the terminals of the grammar because I need to have the same language, so we get that for free. So the only thing I need to worry about now is the set of rules. Okay? Let's see. What's a really easy set of rules? If I'm at a particular state, say P, and I want to know how do I get to P with the same stack contents? What's one way to do it? Could I do nothing? Yeah. So what string did I just generate? The empty string. So, and we'll see a graphical way why this is true. I may have some completely different way of getting from state P back to itself with the same stack type, but one way to do it is to absolutely do nothing. Okay, well that's good. So now what I need to do is I need to relate variables to each other. Because if we just live with these type of rules, then the grammar will be pretty ridiculous at that point. So let's see. I start and end empty. Could I be in the be empty in the middle of the computation? Could I be empty in the middle?
Yeah.
Yeah. Like here, I could be empty. I can't check that it's empty, but I could be empty. Well, let's see. So let's suppose that I'm in state P here. I'm in state Q, some other time it comes down, and R over here. And I'm not supposing that these are three different states. They could all be the same state. And I'm not supposing that the stack is fully empty. I'm just saying that they are at the same stack height, which is something that we would want. Well, let's see. I want to know how to get from P to R. So I want to figure out how do I get from P to R. Could I use Q to help me? Yeah, how can I do it?
From P to Q and then Q to Q.
Right. Just like we did, yeah, we looked it over here. Any string that takes me from P to Q concatenated with any string that takes me from Q to R. I'm supposing I know both of these subproblems, so then I know the solution to the larger one. But the key is, I better ensure the same stack height both times. So, if I can get from P to Q, and I can get from Q to R, then I can know how to get from P to R. It's just a concatenation of any string in here with any string in there. So it's exactly how we are just visualizing it here. Okay. Well, again, If we live with just these rules, then it still is not going to be very interesting. So let's figure out how to introduce the reading parts into it. Well, let's see. Suppose that I'm going to look at this scenario right here. So what I'm going to do is, unfortunately, I should erase this to make room, but let's magnify that area. So let's suppose that I do the first push, or whatever push is right here. It does some stuff in the middle, and then it comes back down. And I know it comes back down because I end up at 0. So sometime I must come down. Well, I'm in states at each 4 of these locations. They may be the same state, they may be different states, but let's just call them names. So I'm going to call the thing I got to go from and to P and Q, and the middle part's R and S. Just arbitrary names. Well, does this transition right here, the first one, does it pop anything? No, it better not, because it's a push, and we'd only do exactly one of the two. So this transition better not pop. And, well, let's see. It pushes something. Let's just say it pushes an X on. What does this last transition do, assuming P and Q are the same stack height? It pops what? An X, right? I'm assuming it's the same stack height. And I'm also assuming that we don't come down to this height in the middle, but that we don't have to worry about that actually. So I'm definitely going to pop in that transition. But do I assume anything about whether I read or not on these transitions? Not necessarily. I may read on them, I might not. So let's just assume that we do read, or we can substitute epsilon for these two symbols. So let's say I read an A on the first transition, B on the second. So what's my goal? I got to get from P to Q. So that's the thing I want to know. Could I use the intermediate parts to help me here? Yeah, how can I do that? Well, what's the sub-problem here? If I know how to get from R to S, do I know how to get from P to Q? Yeah, what do I do? So if I happen to know ARS, getting from R to S, well, how do I get from P to Q then?
P to R to S.
Read it, the character on the push transition, which happens to be an A in this case, concatenated with anything ARS could make, followed by reading a B. So now we can relate corresponding push and pop transitions with the same symbol via reading on the first guy, supposing I know how to get from here to here, from R to S, then going from S to Q. Okay? And that's exactly what we're doing. We're just mimicking the stack height over time. And the thing is, do I know what's going to happen in the computation? Well, not necessarily. Do I know that, say, this transition's not going to be used? I don't know that for sure. Because it's an arbitrary PDA. So we're going to do this for every choice of states and input characters. Okay? Any questions about that? All right, so let's actually do one. So here's PDA, and I want to make the CFG, obviously. So let's figure this out. So what are my variables going to be? Oh, first, I shouldn't do that first. Is the PDA good? Have I made the appropriate transformation yet? Does it have one final state? Yep. But is there something wrong with the final state here? It's reading on the transition. Do the transitions here read? No, because I better have read all the input by the time I get to the original final state. But that final state reads in its final state. So I can't have this guy be a final state anymore. So what do? I gotta make a new final state. So I'm gonna make a new final state Q3. What is Q3 itself gonna do? Yeah, it's going to self-loop doing what? Popping everything off the stack. Well, what are the stack symbols in this PDA?
A and B.
Well, it certainly contains A and B. It could have other things, but for simplicity, I'm going to assume it only has A and B on it. Because the only things that involve the stack already involve A's and B's, so if it had anything else, I don't even care. So Q3 is just going to self-loop, popping A's off and popping B's off. Well, that's fine and dandy, but how am I going to hook up this new final state to the machine? Yeah, the triple epsilon transition we had here, because I don't know that the stack's not going to be empty by the time I take that transition. So I better not do anything on that transition. So now we actually do have a final state that's of the criteria that we want. But am I done or not? Is there something I forget? Are the transitions good? Well, let's see. Do every single transition push or pop exactly one of those two? Well, this one's good, this one's good, this one's good, this one's good. Oh, that one's not good, and those two are good. We're almost there. So we have one thing we need to fix. So I better not have this transition again. But what am I going to do instead? So it did neither a push or pop. So what should I do instead? How did we handle both not pushing, not popping? We push something, we pop something. Does it matter which stack symbol I push? But does it matter what thing I pop? The same symbol. Good. So I'm going to make a new state Q4. Come here. And it's important to note that the original transition didn't read. So both of these transitions are not going to read either. So no read, no read. The first one, let's just say I push an A. It doesn't actually matter which one I push, as long as the second one pops the exact same. Okay. So now we actually do have a PDA that's good. Every transition's good, and we have a single final state that doesn't read anything on its transition. Okay? And it pops all the characters off. Any questions about this PDA so far? So now we're ready to convert it to a CFG. So what are the variables of this, of the grammar that I'm going to make? What are the variables going to be? Well, let's see. It says that we're going to have all choices of P and Q as states. Well, I have 5 states here. So how many variables am I going to make? Don't all answer at once. How many variables am I going to have? How many choices of P do I have? 5. How many choices of Q do I have independently? 5. So how many is that in total? Don't say 10. 25. Yeah. So I'm not going to write all the variables down because even in this small example, the grammar's big. Well, let's see. I got to have all pairs of states as variables. So let's say AQ0, Q0 is 1. AQ0, Q1 is another variable. And then let's say I keep going until AQ4, all pairs. Okay. and it's pretty obvious that I want to make this work in general, but are there some variables in this specific case that make no sense? Yeah, well, which one? There are actually quite a few. What about, say, AQ4, Q1? Is that going to make anything? No, because there's no path from Q4 to Q1. So in general, if your PDA represents a strongly connected directed graph, then every variable will be used. But in this case, it definitely isn't. So some variables will not be used, but I want this to work for every PDA to convert to any CFG. So I want to not delete any variables or be clever about this. Okay? So what's my start variable then? What's my start variable? Q0 and Q3, because that's the final state. All right, that's good. So, and the terminals are good because it's just the characters in the input alphabet, whatever they are, A, B, or anything. But now I got to do the rules. So which set of rules is the easiest to do? Well, I think these ones are really easy, right? So first off, how many rules for this particular PDA are going to be made? How many choices of P do I have? 5. It's always 5. So, how many rules am I going to make? 5. Because the subscript is the same in both cases. So, I'm going to have A, Q, I'm not going to write them all, but Q0, Q0 makes empty. A, Q1, Q1 makes empty. And then all the way down to the Q4, Q4 makes empty. So at this point, you're going to start saying, well, for these guys, we're going to have many more. A program will do this much more efficiently than writing it out. So I highly recommend writing a program to do it. But I promised you a graphical reasoning as to why we have rules like this. Well, let's see. Suppose that we are looking at a situation like this where we have a push or pop. Well, what has to happen if this is the pop that gets me back to the same height? What has to happen is I better have a peak somewhere. I can't go infinitely up. There's got to be at some point where I come to a point. And I can't go flat because every transition pushes or pops, but not both. So when we get to here, am I in the same state in both subscripts? Yeah, I'm in the same state because once I apply a transition, I go to a different state. So here, if I know the string from both sides up to here, I have the concatenation of both sides, and from here to get to right here without taking a transition, I better not produce any characters, so it's epsilon. So that's another reason why we have rules like this. Okay, well, I got to do this second set of rules. So, how many rules is this going to make? Anyone knows cubes, times tables? Please know your times tables. How many rules is this going to make? How many choices for P? 5. How many choices for Q independently? 5. How many choices for R independently? 5. Please don't say 15. How many rules is this going to make? 125. Do you think I want to write them all? No. So, but let's see. Let's suppose I want to know how to get from Q0 to Q3. Well, that's my start variable, so I better know what it does. Well, what do I know about the subscripts of the two variables on the right side? Is there something I know immediately? Well, if I know P and R, I think I know P and R. So the first coordinate of the first variable better be the P, which is Q0 here. So the first one here better be Q0. And for the same reason, the second one of the second variable better be Q3. Because that's the place I gotta get to anyway. What about in between? Could it be any state in the middle too? Yeah, I don't impose any criteria as to which one is a good choice, right? So I could choose, say, Q2. That's a perfectly valid choice. And I actually have to do every single one. So for Q0, Q3, there are going to be 5 rules corresponding to that. Okay, okay, well, let's do another. Suppose I want to know how to get from Q4 to Q1. It makes no sense here. It won't produce anything, but I got to do this in general. Well, from this, I know that the first coordinate of the first variable is Q4. And the second one of the second variable is Q1 for the same reason. And like before, I don't have any choice as to which one is in the middle. Well, I have a choice as to which state, but I have to do this for every single one. So let's say I do it for, I don't know, Q2. But it makes sense because if I want to know how to get from here to here, if I know how to get to an intermediary point and that intermediary point to the destination, then I know exactly how to get from start to end. Okay? Any questions so far? Okay. Well, now we gotta do rules of thumb. So I'm ignoring this part in the middle now. But what things, if I want to make a rule like this, what should I be looking for in the PDA? What's that? Transitions that correspond to each other. Yeah, transitions that, one transition that pushes whatever symbol, and then some other transition which pops the exact same symbol. Well, let's say I wanted to do that transition. Well, it pushes an A. So is there another transition that pops an A? Yeah, there are actually several. So this one works, this one works. Oh, no, not this one. This one works, and that one works. So let's say I do this transition and that transition. I'm gonna make a little program. So I'm just gonna redraw the transitions. So it's pushing an A here, Q2, pop. Okay, well I gotta make the rule itself. So I gotta know what P, R, S, and Q are. So P and R are my starting and ending points on the push transition. So where do I start and end on the push transition? Where do I start on the push? Q0, right? Where do I end? Q0 also. So both of these are going to be Q0. S and Q are where I start and end on the pop transition. Where do I start and end on the pop transition? Q2, because that's the pop part. So I pop, go from Q2 to Q2. Well, let's see. I gotta know how to get from P to Q. Well, what is that? That's Q0 to Q2. Do I read on the push transition? Yeah, I read an A right here. That's what the transition said. So I'm gonna read an A. Now I gotta get from R to S. What is R? Is Q0, and S is Q2. So I gotta know when I get from Q0 to Q2. Do I read anything on the pop transition? Yeah, I would read a P. Cool. And now we just made one of those rules. Okay. Let's do another one. Let's do one that's not a self loop. So let's do Q4 to Q3 for the pop. So Q4 to Q3. I don't care that it's something. And then I pop on that transition. So we got to figure out what my S and Q are for this guy. I'm going to stay with the same push transition, but a different pop type. Okay? Well, where do I start on the pop transition in this case? I start in Q. Please answer. Q. Which one? 4. Thank you. I seriously need to get you all coffee. All right. Where do I end on the pop transition? There's only one other choice. Q3. So now I gotta figure out, how do I get from P to Q? Well, P is Q0 here, and Q is Q3. So from Q0 to Q3, do I read on the push transition? Yeah, I still read on the push transition. I'm doing the same transition. Well, I gotta get from R to S. Well, how do I get from R to S? From Q0 to Q4. So I go from Q0 to Q4. Do I read anything on the pop transition? No, it's labeled up. So I don't put it in. Okay? So what does this mean? This says, in this particular case, if I want to get from 0 to 3, what do? I read an A, which corresponds to taking a self loop, so I'm back at 0. I go from 0 to 4, whatever string takes me to here, and then I read nothing to get to 3, which is exactly what I want. Okay? So all it really is just simulation of all possible computations at the same time. And of course, I may have variables that make absolutely no sense, and the good thing is they'll never ever produce a string. Because the transitions here will only be modeled with the rules that actually generate something. So for the rules that only generate something, it corresponds to actually taking a transition. So I don't have to worry about the variables that take me from some state to some other unreachable state. So it's really nice on how all this wraps up. But are there any questions about this? So I definitely don't have time to do the actual conversion to the next guy. But let's start the, at least make the PDA and you can actually convert it in 12 minutes. So I'm going to erase this and then test your knowledge on whether you remember. All right. So second problem is we want to make a PDA for this language L, which is A to the I, B to the J, C to the K, with I equals J or J equals K. What if I said and instead of or here?
All three are equal.
It's not content free because we showed that in class yesterday. So I better work with or here because I want to make it content free. It's definitely not regular because I can just set k to 0 and make I equals j and all hell breaks loose when you do the function lemma. But I want to make a PDA for this. How am I going to do it? Well, let's see. Is there a particular word here that's important or seems important?
Oh.
It looks like or seems pretty important. What is that? Do you think that corresponds to? It looks like union. Do we know how to do union with PDAs?
Yes.
Yeah, how do I do it?
The 3 epsilon.
Yeah, triple epsilon transition to 2 parts. Yeah. So that's exactly what we're gonna do. Don't push or pop on either. Well, it's not pop, but I won't push either. Because I expect the stack to be empty when I get to each of the 2 parts. Okay, well that's good. So let's say I'm gonna do this top branch, which corresponds to I equals j. So don't worry about j equals k yet. So for I equals j, do I care how many c's are after? If I have the same number of a's and b's, do I care how many c's are after? No, I don't care. So maybe we can employ a strategy for the language a to the n, b to the n, and at the end, just read off c's, and therefore we can be good. So how did we start making a PDA for a to the n, b to the n? What was the first thing that we did? Push a special symbol on, right? Because I want to detect when the stack is empty, which means I've matched the a's and b's. So here, I better not read, better not pop again, but I better push on a special symbol. Okay? Well, like we did before, we're just going to push on the a's, and then when we're going to non-deterministically choose, we're going to start reading b's and match them up with the a's on the stack. So I'm just going to repeatedly read a's and put them on the stack. Non-deterministically choose, so don't read, don't push, don't pop, don't do anything else. And here, same thing that we did before, we're gonna, well, analogous. We're gonna read a B, pop a corresponding A, and push down. Okay? And then, once we're all done matching them up, the only thing on the stack is the $sign. So I better pop that guy off and accept. Because what happens here? I match the A's up with the B's, which means I equals J. But then what do I do with the C part? There may be C's after. Just self-read. Yeah, just read the C's off. Right. So C, do nothing with the stack. Okay? And then now let's worry about the other case, J equals K. So just like before, I don't care how many A's are at the front. So maybe what I can do here is just read off A's arbitrarily. Because I don't care how many there are in this case. And then what do? I'm going to non-deterministically choose to do almost the same thing we did here, but with B instead of A and C instead of B. It's almost exactly the same. So I better push on the $sign. Here, I'm just gonna push on not B's here, sorry, not A's here, but with B's. Non-deterministically choose again. And then instead of B, I'm gonna have a C. Instead of A, I'm gonna have a B. So C, every time I see a C, pop a B off. And then once I'm done matching them up, the only thing that could be on the stack is the $sign, and popping it off, I can determine it that way. And then I accept. But is there anything after I read the C's? No, there's nothing after the C's. So I just come over here and accept and do no transitions there. Okay? Cool. Is this PDA in the right form to convert it to a CFG? No, there's problematic transitions everywhere. So like even on these ones that do, so like these ones we know how to deal with pretty easily. Just put another state in the middle. Here, what we gotta do is make another state, travel to it, and come back. So it's not like before where we went to different states. Here we have to go to the same state. But we do have good transitions like these guys, and the nice thing is that we don't have any transitions that do both push and pop, which is kind of nice. Cool. Any questions about this? So I invite you to convert this to a CFG at home. But any other questions? All right, I'll see you next week.